Here we are in our next to the last chapter of chemistry. This is so exciting. And once again, we're still talking about the atmosphere. We've looked at the atmosphere and the gas laws that govern the chemistry of the atmosphere. Last chapter, we've looked at the composition of the atmosphere and the energy and how it interacts with the solar energy to create the weather patterns and quite possibly uh, the fact that we are putting out so much carbon dioxide into the atmosphere, we may be irritating Mother Earth and causing some of the climate change that we've seen here within these last few decades. Now we're going to change focus. And whereas climate change is an evolving science, that we're still dealing with uncertainties, one of the things that we can talk about in this chapter that is going to focus on acids and bases is acid rain. Very little unsettled science here. In the 1950s and 60s and 70s, we pumped a lot of gases into the atmosphere that mixed with the moisture that you now know. There's a lot of moisture in the atmosphere. Those gases mixed with the moisture to create rain that was unnaturally acidic. One of the first things you must understand is that all rain is acid rain. Because we have carbon dioxide in the atmosphere, carbon dioxide will mix with water and make rain, natural rain, to be slightly acidic. But when we talk about acid rain, we are talking about unusually acidic rain. So let's let Hank Green from Crash Course introduce us to this concept.
Captain John Mullen, there, he blazed the first wagon trail across the Rocky Mountains into the interior of the Pacific Northwest. The captain's only been standing in this spot right here for about 75 years, and look what's happened to his face. I know this maybe isn't the face melting you were expecting, but we're not so gruesome here at Crash Course Chemistry. The sorry state of Mr. Mullen's face here is the result of an acid-base reaction, one of the three major types of reactions that happen in solution that we'll be talking about here at Crash Course Chemistry. And the acid that did this was mostly sulfuric acid. Now you may be wondering, who's been coming by and throwing sulfuric acid on statues? Well, actually, what's been doing the throwing is clouds, the sky, though the actual source of the sulfuric acid, that's 400 miles away at the Colstrip Power Plant in Colstrip, Montana, and also at coal-fired power plants all over the United States. The United States of America burns about 1 billion tons of coal per year, and most of that coal is mined right here in the US. Montana, where I live, is home to the Powder River Basin, a geographical location responsible for 40% of America's coal output. Between 50 and 70 freight trains ship out of the Powder River Basin every day. Each train has at least 115 coal cars and is more than 1.5 miles long. And all of this coal burning, it has effects, significant effects. Acidic effect.
All right, yeah. The coal, and folks, we here in East Tennessee and southeastern part of Kentucky and West Virginia, we're loaded with this stuff. We used to produce huge amounts. Unfortunately for us, the coal that's in the eastern part of the United States is dirty coal. It has a lot of sulfur and nitrogen compounds in it that when burned produces these gases that produce acid rain. So, we're going to do things a little out of order for this chapter. We're going to start out with acid rain. I can describe acid rain including how it is formed, causes, pH, and the effects on the environment. Okay, so where did acid rain start? To tell you the truth, acid rain has always been with us. You got a volcano, you've got acid rain. Okay, acid rain is natural. But when you're talking about this kind of acid rain, you are really talking about the acid rain that was caused when the Industrial Revolution really started about 160, 170 years ago. When did we start detecting the effects of acid rain? Well, where is in Scandinavia and then in the northeast United States. What were some of the environmental effects of the acid rain? Fish began to disappear from lakes. The surfaces of limestone, which you saw that statue, it's not the only statue that's had uh, damage to it. Surfaces of limestone and concrete buildings and marble statues began to crumble. Crops slowly and crops grow slower than normal, and forests began to die out. Let me just very quickly cover this. I think we may cover it later on in our notes, but concrete is mostly made up of calcium carbonate. Calcium carbonate. And when you add any acid to it, like sulfuric acid, it's going to form carbon dioxide and water, and then what we call a salt. In this case, calcium sulfate. Calcium carbonate or limestone is used because it's impervious to normal water, normal rain, but calcium sulfate is easily washed away by rain. So, acid rain converts concrete into chalk, basically. This is a picture taken from Klingman's Dome. What do you see? You see a bunch of dead trees. What killed the trees? Acid rain. No, acid rain did not kill the trees. A teeny tiny little worm called balsam woody adelgid. Balsam woody adelgid killed these trees. Okay, Mr. Marino. So I thought we were talking about acid rain. Now we're talking about a worm. Well, yes, there is a relationship. You see, what happened is that the acid rain that Klingman's Dome started getting would basically wear away at the protective cover that all these trees, especially the young trees, have on them. When it wore away the protective cover, the worms were able to get in and basically suck it dead. So, did the acid rain kill them? No, the worm killed them. What did the acid rain do? The acid rain made conditions more favorable for the worm to get in and kill these trees. This is about 30 years ago. Things are getting much better. Trees are moving in to replace these old balsam or Fraser firs, and those trees are more impervious to the acid rain. Plus, not to mention, there's not as much acid rain thanks to the tireless work of environmentalists and the EPA. There's not as much acid rain hitting the Smokies. That's good, but other species of trees have moved in that are more impervious to this tiny little worm. Here are a couple of, what are they? Gargoyles? No, though I remember that TV show, and that was a cool TV show. These are called grotesques. Grotesques. And actually, the TV show called Gargoyles should have been called Grotesques, because gargoyles are water spouts. So that's where water comes out. Now, I don't know whether in medieval times they thought that by making these water spouts look like demons that you would ward off other demons. I never quite understood that. The fact is that if it is a statue like this, it is a grotesque, and if it is a water spout, then it's really a gargoyle. But what has happened to the faces? I mean, who did these statues? Was it a preschooler? No. As you can imagine, at one time, these were perhaps scarier looking demon-type creatures, but acid rain has literally wore out all the features, all the details in their faces.
So, what does any of this have to do with power plants in John Mullen's face? When coal is burned, the sulfur in it reacts with oxygen to form sulfur dioxide. That sulfur dioxide then reacts with water and oxygen in the air to form sulfuric acid. When that sulfuric acid rains down, a set of acid-base reactions take place that damages limestone and metal and acidifies the water supply, making life harder for fish, coral, salamanders, and pretty much everything else. Limestone is mostly made of a chemical called calcium carbonate. The carbonate acts as the base, accepting sulfuric acid's protons and converting into carbonic acid, the conjugate acid, which breaks down into CO2 and water. Calcium and sulfate ions may precipitate as a salt that's more commonly known as gypsum. Okay. So the average ton of coal burned in America is about 3% sulfur. Supposing 100% of those 30 kilograms of sulfur leaves the smokestack and converts to sulfuric acid, how much limestone could that completely wash away? So each ton of coal burnt by a U.S. power plant produces enough sulfuric acid to dissolve about 94 kilograms of limestone. And as we burn about 1 billion tons of coal per year, it's safe to say that no statue is safe, except for ones built of materials immune to acid, particularly oxidized copper, which will last pretty much forever. Hence Lady Liberty's hand presiding over the Planet of the Apes. So, this is clearly a problem. I mean, not just for statues, but acid rain has killed or harmed huge swaths of forests. So, this is clearly a problem. I mean, not just for statues, but acid rain has killed or harmed huge swaths of forests. At the peak of acid rain problems in the US, the highest recorded acidity was around that of lemon juice, which I can tell you is pretty acidic, high enough to irritate human skin. This first became an issue for power generation when the British House of Lords in 1929 ruled that a power station was liable to damages caused to nearby crops by acid rain. So something had to be done. But what? Well, we already know one very common chemical that reacts easily with sulfuric acid. Good old limestone. And in England, there is lots of limestone. By passing the smokestack gases through a limestone slurry, the SO2 converts to an acid and then reacts with the limestone, forming CaSO3, calcium sulfate. Now we're going to do something a little different for those of you who want to go the extra mile. Assuming that 1 billion metric tons of 3% sulfur coal is burnt in America every year, and all of it is converted to SO2, how many tons of limestone would we need to scrub out 100% of that sulfur? Answers down below in the comments. The limestone scrubber is a good system, but it's not perfect. Many other flue gas desulfurization systems have been developed, and now through a combination of good policy, good science, and hard work, about 95% of sulfur produced in coal-fired power plants in the US is removed before it leaves the smokestack. And through some even smarter chemistry, some of that SO2 is actually converted to industrially useful chemicals, for example, pure sulfuric acid, which is used in paper mills, iron and steel making, industrial cleaners, and chemical synthesis. Chemistry! Causing problems, but also fixing.
You're probably familiar with the coal-fired plant that's just down the street at on Edgemore, and you know there's a big, giant smokestack that is no longer being used. Isn't that cool? Well, why was it big and giant? Well, it was producing this sulfur dioxide and the NOx gas. We'll talk about it. Okay, and we did not want this to come anywhere near our city. So they built this big giant smokestack so that it would get up there into the upper atmosphere and go away and be someone else's problem. Now you'll notice there's a much smaller one, and that's the one that's working all the time because this smaller one has those scrubbers that pretty much eliminates most, if not all, the sulfur dioxide coming out. That is cool. So why is normal rain acidic? Because carbon dioxide mixes with water to form carbonic acid. That's an acid. So normal rain is acidic rain. Well, we're talking about pH 6, pH maybe 5, but that's pretty much it. What are some of the other gases that cause acid rain? Sulfur dioxide, sulfur trioxide, and what we like to call the NOx gases, NO2 and NO3. This is sulfurous, not as nasty as this one, sulfuric. This is nitric, very bad, very bad. And this is nitrous. SO2, SO3, and the NOx. What produces these acid rain gases? Combustion of fossil fuels. We've already looked at that. Sulfur oxides and nitrogen oxides are produced by coal-fired plants like Bull Run downstream. What other problems does acid rain create? Damages our building materials like concrete. Many ancient buildings like the Parthenon. No, not the Parthenon in Nashville. That's a imitation. That's a mock-up. That's a copy of it. We're talking the Parthenon in Greece, which is about 3,000 years old. Well, it's been damaged irreparably thanks to acid rain. Give an equation that explains how limestone or concrete is damaged. I've already given this to you several times. Let's do it again. Calcium carbonate, concrete, plus sulfuric acid forms gypsum. Just think of it as chalk. Carbon dioxide gas and water. Yes, sirree, folks. Acid rain will turn your building surface into chalk. What is the problem with calcium sulfate replacing calcium carbonate? Calcium sulfate will dissolve more in water than concrete. The whole reason why we use concrete is it doesn't dissolve in water. Look it up in your solubility chart. Calcium carbonate is insoluble. Calcium sulfate is soluble. What is the biggest geopolitical problem with acid rain? Well, as I told you, that big giant smokestack's job was to take those gases and have it rain somewhere else as acid rain. So someone downwind used to be very, very angry with us. Of course, we're angry with the people who we are upwind from. Their acid rain falls on us. Our acid rain falls on other people. But when you have places like Europe where you have a bunch of countries all jammed next to each other, then as you can imagine, it's not like Minnesota getting mad at Montana. It would be like Belgium getting mad at France, or like Scandinavia getting mad at Britain. This crosses not just state lines, but national lines, and we've got, therefore, problems. The wind carries the gases to other parts of the continent. So countries getting mad at each other is far more dangerous than states getting mad at each other. As you can see here, the majority of our sulfur dioxide is coming from coal-fired plants. Yes, trucks, cars, a little bit, industries, a little bit, miscellaneous, a little teeny bit. According to the graph on the screen, what is the number one producer of sulfur dioxide? Coal-fired plants. Should we stop using coal? Well, then, yes, but you better expect that your mom and dad's going to have to take your cell phone away because they're going to have to pay a higher price for energy. So you're going to have to decide. Either we keep energy as cheap as possible so that we can keep a smartphone in your hand, or do we make energy far more expensive and use cleaner burning fuels like methane? What will it cost you? Your cell phone. It's going to cost money. It's going to cost money. Coal is cheap. We have a ton of it. Who regulates how much SO2 gases these plants can emit? The Environmental Protection Agency, EPA. They've done a lot of good. Recent years, they've been hit with some scandals, but overall, they've done a lot of good in their time. What law gives them the right to do this? The Clean Air Act of the early 1990s. Clean Air Act. President Obama is trying to amend the Clean Air Act by adding limits to how much carbon dioxide. Well, Congress, which is now controlled by Republicans, are trying to stop that because if you limit the amount of carbon dioxide, then these companies are going to have to spend more money in the technology to limit that CO2. And in some cases, it's just not possible. So they have to buy carbon offsets, which is a really strange thing. It's almost like you're paying somebody to take the blame for you emitting carbon dioxide. So former Vice President Gore is, and a lot of people like him are heavily invested in these carbon. You need to read about it. It's really kind of a strange thing. Was there any progress in the 1990s? Yes, in the late 90s we started seeing a decrease in the amount of acid rain. Yay, good news. What were the reasons for the decline in emissions? Using more expensive, lower sulfur coal, which has been very bad for the eastern part of the United States because we are loaded with coal, but it's high concentrations, or rather higher concentrations of sulfur in our East Tennessee coal. So it's just very, very difficult to burn. So a lot of the coal that we're getting at Bull Run is coming from out west where the coal is clean. We've been using scrubbers, as you see in the smokestacks out there in Bull Run. What is the problem with reducing NOx gases? Well, the NOx is produced by, yes, your car, okay, which is a whole lot more difficult to regulate. But how has this been reduced? Auto industries have installed more efficient exhaust systems which capture this nitrogen dioxide and produces and converts them into solids. Okay, so now you've gotten a little taste of acid rain. Hopefully you now realize several important things. That is that rain is normally acidic. All rain is acid rain. But when we are talking about acid rain, we're talking about unusually high concentrations of acid in the rain. What's causing these things? Gases such as sulfur dioxide, which is found in the emissions of coal-fired plants. As you burn coal, the sulfur dioxide, the sulfur mixes with oxygen and is emitted as part of the exhaust. That sulfur dioxide mixes with water in the air, and it creates this nasty acid called sulfuric acid. Less nasty, but still bad. Sulfuric acid is also produced. Comes raining down, literally dissolves away our concrete, which is a basic building block for us, and damages statues. Even we contribute to acid rain with our cars because they produce NOx. Are we making some progress? Yes, we are. We install scrubbers into these giant smokestacks, which is able to actually encapsulate a lot of the sulfur in the form of solids that can be used in industries, as well as reclaiming lands that have been destroyed by strip mining. I have a friend who works at Oak Ridge at UTK Agricultural Center, which that's what he does. He has been able to prove that some of this waste that is produced by places like Bull Run, in order to that captures the sulfur, that stuff can be used as fertilizers to try to reclaim lands that have been destroyed by strip. Pretty cool. Chemistry creating the problem, chemistry solving the problem.